Hi, everyone. This short talk I'll be presenting is kind of a boiled down version of my master's thesis. So I'll try to rush and try to get everything. But in case I miss something, in case there's some gaps, feel free to reach out to me. I'll be in the back and I'll happily answer your questions. So the title of my presentation today is Evaluating the Combination of Reflectances and Three-Dimensional Point Cloud from Drone Imagery for Detecting Forest Insect Damage. As I said before, this is part of my master's thesis. And here are the different organizations involved. And before I even start with the presentation, I would like to start with the acknowledgements, the section without which this project itself would not have been even possible. The University of Idaho Moscow is located in the homelands of the Nez Perce, Palouse, and Coeur d'Alene tribes. And data for this project was collected in the ancestral homelands of the Kootenai, Pend Oreille, and Salish tribes of Western Montana. I would like to thank my advisor, Dr. Jeff Hickey, my committee members, Dr. Jason Carl and Dr. Arjen Meddens. I'd like to thank Dr. Amanda Stahl, University of Idaho Ecological Geography Lab, the Washington State University Forest Ecosystems Dynamics Lab, and the Forest Service's Rocky Mountain Research Center as well. So first I'm going to present to you a brief, very short introduction slides to set up the background. So remote sensing is a very common tool used in the detection and monitoring of insect disturbances. One of the main advantages of remote sensing is the availability of data at various spatial, temporal, and spectral resolutions, as depicted here on the figure on the left. And forest insect disturbances are detected and monitored with the remote sensing of characteristic tree damage. And some of these examples are on the figures on the right, as in tree mortality, discoloration, defoliation, and branch flagging. These often correlate to specific forest insect gills and also can correlate to stage of insect infestation. So this is how we remotely sense forest insect disturbances. And going more into the specific, for this talk, I want to talk about remote sensing with uncrewed aerial systems or drones. An additional advantage with remote sensing with drones is that there's the possibility of collecting three-dimensional point cloud data using techniques such as structure for motion photogrammetry, where the individual drone images collected as shown on the figure on the right, on the top portion, can be used to reconstruct a three-dimensional point cloud. And the three-dimensional point cloud provides structural representation of objects on the scene. And here you can see the structure of a tree, which I'm studying. And so the objective for this project was to evaluate the utility of structure for motion point cloud for the detection and monitoring of forest insect disturbances. And there were three main objectives or stages for this project. The first one was segmentation of individual trees, separating individual trees. This is the most common use of point clouds in forestry and remote sensing of tree health. Second one is the classification of points, where I classify each individual points as healthy or damaged. And the third one is combining 1 and 2 and assessing the damage on each individual tree itself. So the first stage, segmentation of individual trees. As I said before, this is the most common use and it's very well established, where I separate each individual tree on the point cloud. And I did this in R. And this is just a subset data where each repeating color represents a segmented tree, a separated tree. And as I said before, I did this with established techniques in remote sensing of tree health. The second and the more novel approach, second and third, is the classification of points, where I classify each individual points using random forest modeling. And for this, for the model training and evaluation data set, I had a data set of points that represented green class, points that represented red class, gray, and points that represented shadow class. Here, the green class represents the healthy points, and the red and gray represent the damage points, and shadow is shadow. Each of these points contained reflectance values in blue, green, red, near infrared, and red edge, and also spectral indices. And I use this information as input for the random forest model that I trained. And this random forest model had outputs of classified points of green, red, gray, and shadow. And then after I selected a good high-performing random forest model, I applied it to the study area. And this is what it looked like. If you zoom in, and as you can see, each of the points were classified as healthy and damaged. Moving on to the third objective, what I did was I used the product from objective 1, tree segmentation, and then I used the model from objective 2, the classification of individual points, and I combined them. And when I combined them, I got this intermediate product of classified points with segmented trees, and I used that to isolate the point cloud of each individual tree. And then with that, I analyzed the location of damage on each individual tree, going from the top of the tree, as you can see in the animation, and analyzing each height bin of that tree to see where the damage started, stopped, and ended, and based on that, classify those trees into different damage classes. And when combining those three objectives, I get the following products. First, I got tree level damage maps, where each tree was classified into healthy, top kill damage, non-top kill damage, and fully damages in snags as well. And as you can see in the figures, there are clear hotspots, spatial clusterings of healthy and damaged trees. And when you zoom in, you can see that each polygon represents a segmented tree, and each of those polygons are classified in healthy, top kill, and the different damage classes, as well as the percent damage as seen on each tree. You can see some examples here where from the top-down view, you can see a snag that's a fully dead tree, all gray. You can see on the picture that it looks all gray. For top kill trees, you can see that there's a gray center that indicates damage and a green outside, and that correlates with the damage classification, as well as the high percent damage is seen, and same for the healthy trees as well. And so, conclusions from this novel project is this study presents a novel methodology that analyzes tree health status in a three-dimensional environment, where I first classified each point in the point cloud, and using the segmented trees, I analyzed the damage along the height of the tree, the location of the damage, and when I applied these to the study area, I got a damage classified point cloud where each point was classified with high accuracy, 98.6%, and tree level damage maps where trees were separated into healthy versus damage with high accuracy, 93.5%, and different damage types with moderate accuracy, 81.3%. Oh, I finished on time. Do you have any questions? So for the training data, I use this software called Cloud Compare, where you can upload your point cloud, and I individually picked each point. So my training data consisted of 800 points, 200 per class, and I use it. So for that, I have a reference data set of trees that I use the top-down view orthomosaic, as well as the individual drone images where you can see the total height of the tree. And from that, I created the training data from there with field observations as well. So you basically classify by eye which tree that? Yep. Yep.
Can I have you ask into the microphone?
You used a drone to capture the SFM cloud data, but which program? You said it was the Cloud Compare?
So Cloud Compare was used to just see the data in three-dimensional space, but for the drone data processing, it's Agisoft Metashape Professional.
I have a question.
Yes.
What do you do about issues like tree damage, but it's not insect damage? It's like drought or some other symptom. How do you tease that out?
So yeah, I probably should have mentioned this before. This is just a proof of concept novel methodology. And so detection and attributions are two different and very, I would say, hot topics. I would say this method can probably detect it well, but attribution, that needs a lot more ancillary data as well.
Reflection and reflect data into your analysis, or just the LiDAR?
Yes, so for the training and evaluation points, each points had 5-band reflectances as well as 7 indices. And I did a variable model selection with my random forest from one variable random forest increasing, and I selected the random forest model with the least variables but with the highest accuracy.
So how do you apply this reflection data to the point? Because the reflection data is a grade data, right?
Mm-hmm.
The raster and the points data are the points.
Yeah.
It represents a circle of the area. Mm-hmm. So how do you?
That's transfer? A good question. So I use the software Agisoft Metashape that uses this thing called depth maps that is a representation of the depth of an image in three-dimensional space, and from there it uses I'm pretty sure it uses a mean reflectance for that point. So it's not an exact reflectance for each point, it's a mean reflectance from different images collected.
Oh, thank you. But because the points with have a different layers, right? But the reflectance can just see the top layers of the points.
So what happens with structure for motion point cloud is you get different angles of the same image, because when you fly the drone, if this is the tree, it takes pictures here, 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 and so you get the whole profile of it. And therefore, you don't necessarily just sample from the top. You sample from the sides as well. Whatever reflectance the side features gives you.
Thank you.
Okay, thank you, Abhi. We're going to go to our next speaker.
Thank you.
Okay, next up we have Ryan Town.
Thank you. Hi, everyone. My name is Ryan Town. I'm a junior here in the Department of Earth and Spatial Sciences. Thank you to the organizers and volunteers for the event today and the opportunity to talk about my research. I'm here to talk about a research opportunity I've become a part of over just the past semester. I'm working in Dr. Zhao's eco-hydrology lab. We're part of a project that's using state-of-the-art technology, remote sensing data and modeling to understand and improve predictions in different aspects of the water cycle, especially groundwater fluctuation and plant-based processes here in the Snake River Basin, located mostly in Idaho. Our lab understands that humans and communities need water. Most Idahoans depend on the Snake River for everyday water use, and as a community and a state, we depend on water for agriculture, recreation, power, and many other things. As our climate and population grow, our understanding of these processes and predicting the availability of water are going to become more important. One of the main significant sources of water and indicator of water availabilities is rivers. And because of the importance of the Snake River to Idahoans, our project is interested in predicting how much water will be produced by the Snake River under future climate conditions. We also focus on the Snake River Basin because it's a good size. It's a large region with a lot of different land cover types. Here we see it's mostly rangeland, but we also have some forest and crop and urban areas scattered throughout. The basin is almost the same size as the entire state of Idaho, but it's also a convenient size so we can take measurements with some certainty, like stream flow and different climate factors. The first step of predicting stream flow is understanding the factors that drive it. Most watershed assessments assume the precipitation is the main driver of stream flow. As the main input, the only input to the watershed, we would think it would give us a clear picture of what's going on with the stream. But when we plot our monthly stream flow data against precipitation amounts, at least in the Snake River Basin, we see that this is not the case. We don't see a strong correlation between precipitation and stream output. Luckily, in our lab, we utilize brand new methods for estimating water storage, like groundwater and reservoirs. We use data from NASA's GRACE mission, which is 2 robots in space playing microwave laser tag. And they're basically measuring distance from each other, which tells us a little bit about gravitational anomalies and groundwater flux in the Snake River Basin. And when we compare stream flow to groundwater fluctuation and groundwater inventory fluctuation, we do see a stronger correlation. So we see that in the Snake River Basin, stream flow has more to do with groundwater processes and plant surface interactions than it does with precipitation. So with our better observations of total terrestrial water storage, and we have good measurements of precipitation and stream flow, all we need to predict stream flow in the future is better measurements of these evapotranspiration sub-processes. Unfortunately, we don't have these measurements. They're pretty hard to quantify, and a lot of times we rely on proxy measurements and calculations in our water balance equations. So we end up making a lot of assumptions about plant processes and soil processes based on a water balance equation. So we have a better quantification of groundwater. So on the water balance, we're able to actually quantify the amount of water involved in the water balance without having to make those assumptions about processes of plants and surface, in plants in the surface. But since we can't measure those things, our lab needs to turn to more modern tools to tackle this problem, to understand those variables, and to create solutions that are scalable and transferable to new basins. So we're going to utilize the NOAA MP model, which is a land surface model developed through multiple scientific organizations like NASA, NCAR, NOAA, and test different variables through the model in the basin. So our hypotheses center around the fact that that stream flows has more to do with these soil processes and surface level dynamics. So previous research has shown that we can measure soil saturation in our ecosystem with GRACE data. And we can also measure through other remote sensing data, the soil structure and some of the plant hydraulic interactions. So how plants get water from the ground and move it either to themselves or the atmosphere. By using these, the newest models and the newest ways to measure the earth, we're going to begin to experiment with the parameterization of these variables, I guess, in the model, and that'll help us to test conclusions or test hypotheses about the real world. The NOAA model utilizes dozens of static and dynamic data points at a high temporal and spatial resolution. So a typical model run takes thousands of files and tons of computing power. So another exciting facet of our project is that we're able to utilize the Falcon supercomputer located in South Idaho. And almost all of our work so far, so utilizing or installing the model, pre-processing data, and then setting up parameters to run the model are all done remotely and with the help of the team located in South Idaho. So we're excited about this part of the project. It's allowing us to complete some of these calculations in a fraction of the time it would have otherwise. And right now we're sort of wrapping up the pre-processing phase of the project, and we'll begin running, tweaking the variables on the model and running different scenarios and seeing if we can come up with some better conclusions about how to predict stream flow in the Snake River Basin. And that's it, I guess. Any questions?
Any questions? I'll ask a question. So I was surprised that there was no relationship with precipitation and stream flow. Is that very common, or why is what makes I guess why?
Sure. Yeah. One thing that we think is that this may be a situation that is more unique to areas with high soil saturation fluctuation. So since this is an arid environment, the soil can dry out in between precipitation events. So I think that might have something to do with it, but we're really not completely sure yet. I mean, that's what the project is about.
Thank you. Any other questions here? Tyler, anything online? No? Okay, let's thank Ryan again. Our next speaker will be presenting virtually, so we'll get Eric Wing to share his screen.
Can you hear me okay?
Yep, we can hear you.
Okay. I actually don't have any slides to show for this. What I wanted to do is wish everybody a happy GIS Day from the Northwest GIS User Group. And we just wanted to take this opportunity to let everyone know about what's going to be coming up for 2024. So first off, for our new professionals, which we're going to include students and basically anybody within the first 5 years of their GIS career, in January, we're going to be taking applications to select a community member to participate on the Northwest GIS board meetings for the year. The intention is to provide a mentorship opportunity to learn about, well, how do we operate the board and really get an understanding of all the work that happens behind the scenes with the conferences and the events that we put on for a community. With any luck, we will be eventually training somebody that's going to replace somebody that'll be on the board. The deal is, at the end of the year, that individual will present at the fall conference and talk about the experience. So the idea is really just to provide an opportunity to say you don't have to be involved with GIS for 20 years before you start getting involved with the community. And you could learn good and bad and otherwise from how we run the Northwest GIS User Group. Next, if you're going to be at the Esri Developer Summit in spring or at the Esri User Conference this coming summer, you're definitely welcome to attend the social events that we host, and it's open to all Pacific Northwest GISers. And lastly, our 2024 conference is going to be in Seaside, Oregon in late September. The conference organizers are looking for volunteers to help with the assorted aspects of conference planning. So that's something you can get involved with right away. And we'll also be putting out a call for presenters in early spring. And we very well might twist some arms of some of the presenters we're seeing today. This is great stuff. Information on these events will be posted to the Northwest GIS website as the plans solidify. That'll be at nwgis.org or just Google for Northwest GIS. But if you have any immediate questions, you're always welcome to contact me directly at my work email, which is ewing@cityofboise.org. With that, just wish you happy mapping and enjoy the rest of the conference.
Thank you, Eric. And we're going to provide one more additional announcement about upcoming events from Wendy here.
Hello, I'm Wendy Largent. I am one of the co-conference chairs for the 2024 Northern Rockies EURISA conference. And that conference will be held in May, in the middle of May. And we are also looking for presenters and student helpers. And we have the ability to provide four student volunteer spots with a $500 stipend for helpers. And we'll be putting out a reminder of that in January, and criteria for the application. And we're also looking for ideas for tracks for the conference. If you have any ideas or you'd like to help in any way, just come and see me sometime today, or you can also go to our Facebook page, which I do not have the exact link for right now, but you can Google that. Thanks.
Great. Thank you, Wendy. So now we have another break until 11:20.